Okay, so I'm Jane Liu, and the title of my talk. My area of research is small bodies of the solar system, in other words, comets, asteroids. Planets and exoplanets usually get all the attention, but I would argue that it's the small bodies that carry the most fundamental about the nature of planetary system. Why is that? That is because they are what is left of the planetary system. They form throughout the protoplanetary disk, so they serve as probes of the local environment where they formed. There's a lot of them. They get thrown around by planets, and this is both a good thing and a bad thing. It's a good thing because they're thrown around everywhere. It makes them more accessible, and it's a bad thing because where you put them now might not be where they form. And an obvious example of this is comets. Comets form far away from the sun, but their eccentric orbit bring them close into the sun where we typically absorb them. But we know that comets did not form near the sun. So as I mentioned, these small bodies in our solar system and in other planetary systems get thrown around by planets. And some of them just get ejected completely out of their planetary system. And in their subsequent interstellar journey, some of them happen to go through our solar system very briefly. And we have found two of them to date so far. So two interstellar objects have passed through our solar system in the last 5 years. The true number is much, much bigger, on the order of thousands, but that we identified in the last 5 years. Exciting news in the last few years. Thanks to NOT's extraordinary responsivity, we were able to observe the interstellar as soon as discovery announcements were made, and NOT did the same thing. Several comets and asteroids in our own solar system. And in this talk, I will try to show you NOT was the key to us being science that we wanted to do. In our solar system, small bodies are divided into two: comets and asteroids. This is a comet, 17 observed by NOT just a couple of weeks ago. Comets are full of ice because we know that because their water ice sublimates the sun. So this means that comets must have formed somewhere far away from the sun, somewhere in the outer solar system, far beyond the snow lines, so that they were able to incorporate ices in the interior. When they get heated by the sun, meaning when they come close to the sun, they conveniently outgas, allowing us composition. So this is why a comet looks kind of basically like this, with a big fuzzy thing, which we call the coma. And the coma is just a big cloud of dust particles and gas molecules that ejected out in the sublimation process. In contrast, asteroids are inert, rocky bodies. They form in the terrestrial region, well inside the snow line, so presumably no ice. And we believe, up until recently, that asteroids should be of ice because any primordial ice should be lost by now, solar heating and heat by radioactive decay. And here are some pictures of asteroids by spacecraft. As you can see, they look basically chunks of rocks. They're inert. They coma. There's no activity. They're basically just point sources. Look at them through the telescope, point sources. And indeed, the presence or absence of a coma is a traditional distinction between comets and asteroids. But not too long ago, a new group of asteroids, about 10 years ago, basically tells us that our assumption that asteroids being void of ice, and this group of asteroids is called the active asteroids, and some of them are shown here. As you can see, they're not points. They all have coma. They all have basically various degrees of activity. And so that's why they're called active asteroids. Another pretty picture. They tend to make very pretty pictures. So the newspapers like them a lot. So this is an active asteroid, 2013 P5, with spectacular tails. This was taken by the Hubble Space Telescope. Well, the obvious question raised by these active asteroids is, are they really comets, but just simply classified asteroids? after all, if we go by the presence of a coma as a distinction, well, the presence of coma depends on how far they are from the sun, and often it depends on the telescope that they are using. So are these active asteroids simply comets being misclassified? And the answer is no. And I will show that the comets and asteroids in our solar system occupy two very distinct dynamical groups shown here in this picture. So it's kind of a busy plot, and I will show bigger. So the y-axis is eccentricity of the orbit, so basically how elliptical the orbit is. The x-axis is semi-major axis of the orbit, basically how big the orbit is. And you can see, so there are basically two circles of two colors. The yellow ones are the asteroids. The blue ones, they're the comets, and they occupy two. The asteroids live in this area. They're very localized. They live in the asteroid belt located between Mars and Jupiter. And they occupy this very local region bounded by these two curves. And these two curves just indicate the orbit of Mars. In contrast, the blue circles, these are the comets. They're way over here. So they have big semi-major axis, big eccentricity. In contrast, the asteroids have a very small range of axes and small eccentricity. So asteroids and comets occupy. And there are few colorful dots among the asteroids. And so you can see they firmly belong, these active asteroids firmly belong in the asteroid belt. Asteroid that suddenly one day decide to mass. So by this point, we know about 12, 15 active asteroids. And we notice a bunch of them tend to be located near the outer edge of the asteroid belt, suggesting that maybe might play a role in the activity. In which case, if that is true, that would indicate that water ice is still present, asteroids, and it's not that far beneath the surface. And if that's true, that raises the possibility that water ice and other ices perhaps are still prevalent inside the asteroid belt, in spite of all the heating by the sun and radioactive decay. And that it raises an even more exciting possibility that maybe these asteroids are contributed a significant part of water after Earth. A lot of my work is going after these unusual asteroids, other comets, while they're outgassed, because catching them while they are losing mass tells us something about the nature of this mass loss. For example, we want to know where in the orbit did loss start occurring, how much mass loss, how much mass were these things affecting, how fast were the particles traveling. All these questions help us with one goal. That goal is to determine why the asteroid lost mass. And whatever mechanism is responsible for the mass loss, whether it's water ice sublimation or thermal fracture or whatever mechanism it is, tells us something about the asteroid itself. So this picture is a picture of asteroid Bennu. It was taken by spacecraft, Rex. So it was taken about this picture was taken about a few years ago. So when the spacecraft got to Bennu, it was very surprisingly and unexpectedly, it discovered that Bennu was losing mass. And guys in the back probably can't see it, but this picture shows a few white little dots. So the particles detected by spacecraft, particles in Bennu. There are very few of them, just a few hundred dust particles, and they came out first. This was very unexpected, and it raises a very important question. All asteroids, some level, because a few hundred particles like this, no way. So this was only by spacecraft, and again, that all asteroids at some level. And this is an important question because, as I mentioned earlier, it might, if water ice, the role in this, that it would imply that ice is still prevalent inside the asteroid belt, and the asteroid might have supplied part of the inventory of volatiles on Earth. And the other important thing is that all this does go to the cloud, supplies a zodiacal cloud. And if this is happening in our solar system, probably exoasteroids are doing sustaining the debris often other planetary systems. Most recently, thanks to our ongoing targeted program, we solved the case of mass loss in this particular asteroid, 478 Gault. And you can see Gault has a very long tail, and all the other trail things tracking asteroid. So Gault is just a normal main belt asteroid with a radius of about 4 kilometers, and it suddenly decided to grow a tail toward the end of 2018. And so the discovery announcement was made in early 2019. Immediately, to look at it, this was in January 2019. So let's look at the left picture. A month later, we looked at it again, and by this time, Gault has grown a second tail. Now tail A is your tail. You can see that tail B is brighter than tail A, and it's shorter than tail. That's simply because it was ejected. We haven't had and grow very long. A month later, in March 2019, we noticed that the Earth was crossing the projected orbital plane of Gault, i.e., able to look at the asteroid edge on. And so here's a picture that we took when the Earth was crossing the orbital plane. So you can see, you don't see the two tails anymore because the two tails are completely different with everything edge on. And being able to look at the dust tail edge on, because then we were able to calculate, basically measure, the vertical extent of the tail. So we did that, and that turned out to be like 1,000 kilometers. So now we know the vertical extent of the dust tail. We also know when the turned on. Formation, we were able to calculate how fast. Well, and that component would be the velocity component. That turned out to be a very small, 0.1 meter. Can walk much faster than that. So the perpendicular component of the velocity, dust velocity, perpendicular to the orbital plane, is 0.1 meter. This number, 0.1 meter per second, is 10 times smaller than the escape of some size of Gault. So what this means is that the velocity of the dust is predominantly, which is consistent with centrifuge coming out from, being ejected from the equator region. So what this means, most likely, Gault was spinning very, very so fast that the centrifuge were comparable to, or even greater than, the escape speed. In other words, what we say is, in our jargon, we say that Gault is a state of rotation. We were able to rule out other causes for Gault's mass loss. For example, we were able to rule out impact. One impact there's no way one impact could cause three. So you might say, well, what about three impacts? Okay, there might be three impacts, but the odds of that happening. We could rule out water ice because the asteroid were near, in this orbit very near the sun, so it couldn't have the sun very much. We ruled out thermal fracture by, again, it wasn't very near the sun. So basically that just left rotational instability. The most basic test of the rotational instability hypothesis is to measure, and the traditional way of measuring the rotational just to get the light curve of the object. So if you assume the object is aspherical, most comets and asteroids are. So if you take an aspherical body, like an egg, and as it rotates, it will appear brighter periodically. It shows. So when the big cross-section faces you like that, you might appear brighter, and when the small cross-section faces you, it will appear dimmer. It appearing at bright and dim. So one full rotation would have maximum. And then the amplitude of the light curve would tell you something about the axis ratio, the shape of this thing. So you can assume this is a biaxial ellipse. Work a very simple relation that the amplitude of the light curve tells you axis ratio, how aspherical these things are. But you have to know when to light curve. So this light curve on the left was done, this is a Gault, was done in January 2019, as you can see, flat. Okay? Because this was because at the time the activity was so strong that the cross-section of the dust completely overwhelmed the cross-section of the nucleus. So there was no, so the modulation, the brightness variation of the nucleus was not even possible, was not discernible in the middle of this scattering by the dust coma. So we were monitoring this thing thanks to our targeted opportunity program. And 18 months later, in August 2020, noticed that the activity had died down. So we monitored it again, and we were able to measure the light curve in August 2020. And here you can see the light curve is no longer perfectly flat. There are ups and downs, peaks and valleys, and somewhat periodic. The difficulty in making this measurement was that the amplitude of the light curve was asymmetric. At the peak, it was about 300 from top to bottom. But so it resulted in a noisy light curve, but we were able to measure the rotation period. And that came out to be about 2.5 hours. So this is pretty fast. A 2.5-hour rotation period is pretty close to the critical period at which an asteroid, which is basically fast, that would just, so this a rotation period of this magnitude, 0.5 hours, basically supporting evidence for the rotational instability hypothesis. Well, presumably, Gault was not always spinning fast. So that because it survived until now. So what made it spin up to what? Okay. Well, most likely is something called the Yorp effect. Yorp stands for Radowski-Oki, some Russian name, and Padak effect. Well, basically it's like this. If you assume the object is an aspherical body and is heated by the sun, it radiates thermally. But as the thermal photons escape from the small body, they give little kicks to the small body. And if the body is aspherical, these little kicks don't cancel out, resulting in a changes the angular momentum, the spin period of the object. The object could spin up, it could spin down. If it spins down, that's boring. It just gets slower and slower, so nothing happens, no big deal. But if it spins up, then it gets more exciting because it can spin up so fast to the point where it will split itself apart. And this, we believe, is Gault. And this doesn't work on all bodies. Obviously, it works. It's most effective on small ones, during the rotation period of small things, and on things that are close to the sun, get hotter. So anyway, so we think the Yorp spun up Gault. Okay, so besides that, that was one result. Another interesting result we got with NOT was the observation of the first interstellar object, Oumuamua. So when the discovery announcement came out, I emailed Thomas Augustine. I said the first interstellar object had been found in our solar system. We look at it, and the answer was, go look at it. So we did, and we were among the first people to characterize the thing. When Oumuamua was found, everybody expected it to be, and the reason is the following. We know that our solar system had ejected lots of things into interstellar space because we have a belt, we have asteroid, 2 comet belts, and a bunch of planets throw them around. The comet, the asteroid belt, this guy ejected about 1 Earth. The Kuiper belt, 1 comet's reservoir located just beyond Neptune, ejected a lot more, 10 to 100. And then the Oort cloud. This is very uncertain. We don't know that much about it. And it could have ejected anywhere between 1 and 100. So it's uncertain, but you put all the numbers together and you come to the conclusion that the comets outnumber by a factor of 10, or maybe 100 to 1. And if all planetary systems do what our solar system does, then we would expect that interstellar space, which is littered with comets. So with the NOT, we took pictures of Oumuamua, and like everybody else, we will coma because that's what we expected. And these pictures, the top and the bottom is the same picture. It's just the top one has the star trails, and for the bottom one, we took away the star trail to make it look prettier. So this was a stack of 12 exposures, 120-second exposure. The thing was moving so fast, right? At that point, it has already come closest to the sun. It was moving away from the sun at the phenomenal speed of very, very fast. So we couldn't integrate very long. Stack the images together and try to detect a coma, and we didn't see anything. There was no coma. And we were able to calculate an upper limit to the cross rate. We measured its light curve. Looks like this, very pretty. The the rotation period was 8.3. Nothing special. But what was special was the light curve amplitude. It's enormous. Right? This enormous light curve amplitude with more than like several magnitudes implied a very aspherical body with an axis ratio of at least 6. This is much more elongated than anything we've seen in the solar system. So as I mentioned, every single telescope on Earth was pointing at this thing, trying to do the same thing. And this is a composite light curve obtained by all the groups put together. And they showed a periodicity, but they could not be fit with one single period. Everybody came up with a different number between 7 and 8, which is surprising because if you guys could see the legend, right? This was done with the VLT on the left, then Gemini, VLT, and Keck and so on. All the biggest telescopes pointing this thing. Everybody got a different number. Nobody knew what was going on. 2 years later, I think we figured it out. The reason nobody succeeded in measuring one single rotation period was that there was no single rotation period. The thing was slowing down. And so here I plot the 4 data points obtained by 4 major groups, and the point to the right is the not data. And you can see, so the y-axis is rotation period. The x-axis is time. The rotation period was slowing down, so it increased with time, and at the rate about 0.2, pretty fast. So this was just 1 week. 1 week, the rotation period changed sufficiently that one period could not fit the data. So 2 years after Oumuamua came by, the second interstellar object, Borisov, was discovered. Discovered at 38 degrees from the sun, Borisov was really a triumph, small telescope. There was no big telescope. Nott was one of the very few, probably the largest, able to look at Borisov. And Borisov was definitely a. And here's some pictures of Borisov taken by Nott. So thanks to Nott's extraordinary pointing capability, we were able to observe it at air mass 8 in full scattered light from the full moon. And our exposure time was cut short because of the rising sun. But in spite of all those hurdles, we took some very pretty pictures. We measured its light curve. And again, here, it's a more example of completely flat light curves. Again, due to the fact that the cross-section, the dust scattering was completely overwhelmed the cross-section. But we were able to measure how much dust there was in the coma as a function of time. And the x-axis is time, so the y-axis is scattering cross-section. So the coma was getting brighter and brighter with time. And all we did was just extrapolate backward to see when did the activity. And we found that the activity turned on at about 4 or 5 AU, exactly where we would expect water eye to start sublimating. And here's some colors of Borisov and Oumuamua, and it's a busy plot. But basically, the message of this slide is just that colors are basically as the colors that we comets and there was nothing special about their colors. So people tried very hard to pinpoint to find something that would show that Borisov was different from our comets. But they couldn't find anything. And based on what we found, we could just say basically 3 things. One of all, it formed on the snow line of its planetary system, so it incorporated ice. Its activity started where water ice started. It was driven by water ice. And there was some mechanism to eject it from its planetary system. From planets. So all these things, exactly what? Very different. So I'll just wrap it up. So we study the small bodies because they tell us something about the origin of how these things form and how they are destroyed. And we care about them for our own solar system. But presumably anything that happens in our own solar system also happens around the other planetary system. And they sustain the debris of the planetary system. Well, the study of these objects require a very responsive telescope because the activity changes unexpectedly. You can't predict what's going to happen. So we need a telescope that is responsive and is versatile. And these are the 2 qualities many telescopes do not possess and at which Nott excels. So here I show what Nott offers our monitoring program compared to what Keck would offer us. So what do we need? We need a telescope that's capable of immediate response to alert. Not can do that. And there's no way Keck will do what I asked it to do. The telescope should be capable of observation at very high air mass, and not like Keck can't. Should have flexible scheduling, not does it, and Keck can't. Should be capable of non-sidereal tracking, because all these things move, not can do it, and I think Keck can too. The ability to download up-to-date ephemeris from the web, not can do that, and Keck can't. Flexible instrumentation, again, yes but not, and so the conclusion I have to draw is that in spite of not modest size compared to 10-meter telescopes, it outperforms the large telescopes. Right? So there will always be a need for a telescope. I would say it's a pretty good model for the telescopes of the future.